Hey everybody, welcome back. So in our last video, we looked at examples of the empirical rule, right? We were able to answer these questions, like what percent of values are within an interval, right? Based on the normal distribution that we were given. So now let's try to answer one of these other questions and see if we can do it or not with our empirical rule. Excuse me. So up here, let's say we take this first one and let's assume that commute times of students to school from their homes are normally distributed. They have a mean of 18 minutes and a standard deviation of 3 minutes. And we've got some questions here, like what percent of students take between 11 and 23 minutes to commute to school? Okay, so let's draw our distribution. Right. So we have a mean of 18 minutes, so we'll put that at our center. We go one standard deviation to the right, we'll add our standard deviation of 3 minutes to our mean to get 21. We go 2 standard deviations away from our mean to the right, we'll add 3 to 21 and get 24. And lastly, if we go 3 standard deviations away, we add 3 more to 24. We get 27. We do this again on the left. This time we subtract 3 from our mean to get 15. Subtract 3 more, we get 12, and 3 more to get 9. 3 standard deviations below, 3 standard deviations above. Okay, so we want to see what percent of students take between 11 and 23 minutes to commute to school. So let's try to find the area under the curve. And 12 and 24, right? So 11 is just a little less than 12. So it would be somewhere right around here and between 9 and 12, much closer to 12, right? This would be our 11 that the question is asking us for. And 23 would be in between 21 and 24, right? Just under 24. This is the 23 that we're asked for. And what do we need to do to answer this question? We need to find the area under this portion of our normal distribution, right? Everything in here. But what's the problem? Our empirical rule tells us the percent of data, right, that lies specifically between standard deviations, right, of our normal distribution. So we could answer a question like the percent of students that take between 12 and 24 minutes, but that's not the question, right? It wants to know the sorry, y'all. The area from 11 to 23. And so we can't answer this kind of a question just with the empirical rule, right? We could say, well, it's 1 away from 12, 1 to the left of 12, and it's 1 to the left of 24. So why can't we just assume sliding everything over to the to one spot would be the same. Well, you've got different heights here and here, right? So you can't assume that it wouldn't be the same exact area under the curve. So we've come to the end of an empirical rule. The empirical rule doesn't help in the previous problem because the values of interest in question do not align with the standard deviation values. So what do? We need to convert our values in the normal distribution that we're given to something called the standard normal distribution. We've actually seen this before in one of our slides. So we'll convert it to the standard normal distribution, and then we'll use the converted numbers to find the area under the curve of the standard normal distribution. And the area under the standard normal distribution will be the exact same value as the area under the normal distribution that we started with, because all we've done to it is convert it, right? Think of this like converting hours into minutes. I can say, this video is 1 hour long. Don't worry, it probably won't actually be an hour. Or I can say that this class is 60 minutes, right? Those values mean the same thing. That's all we're doing here, right? Is we're just converting a normal distribution into a standard normal distribution, but the area under both of those normal distributions will be the same value. Okay. So so here's a standard normal distribution, right? Again, it's the exact same thing as a normal distribution, except the standard normal distribution always has a mean of 0 and a standard deviation of 1. Okay. All right, so the way we go from any normal distribution, right, with any mean, any variance, or standard deviation that we're given in any problem to the standard normal distribution, right, always having a mean of 0 and a standard deviation of 1, we use something called the z-score. So this is the formula. You take x, which is the value of interest, right, that you're asked about. This would be, for example, right, what percent of our gorillas have a lifespan of less than 23 years, right? X would be equal to 23 in that case. You subtract that value of interest from the population mean, right, the mu of the normal distribution we're given. So if we're given that the gorilla's lifespan is an average of 25 years, right, we would take that 23, subtract it from the average, and then we would divide it by the population's standard deviation. Yeah, so down here in this example, the X value is, what percent of students take less than 14 minutes to get to school. 14 here would be the X value. Think of this as any other conversion from hours to minutes or feet to miles, etc. Right, usually in these types of conversions, you only have one variable that you're converting, right? Hours is going to minutes, feet is going to miles. And how do you normally convert those things? You either divide or you multiply, right? So here we're dividing by our standard deviation. But we have two variables, right, that we need to convert. We've got our population average, which we need to get to 0. So how do you get it to 0? Well, you just subtract it from itself, right? The population mean minus the population mean is equal to 0, right? And then dividing by the standard deviation, or if you were to divide by the variance itself, right? If you just divide this by itself, you would get to 1, right? So that's kind of what this formula is doing, just to help you kind of understand it, understand why we're doing this. Okay, so now what do we do with the z-score that we have calculated? We look up the z-value in this table. So you can see in the top left, whoops. Top left of this table, this z here, right? So these values all down this column are different z values. And then for the first two, right, places, the 10th place, right, the whole number, the 10th place, and then going to the right gives us the 100th value of a z-score. And so what you do is you find your z-score. Let's say our z-score that we calculated was equal to 1.25, right? We took our x value, subtracted it from the population mean, divided it by the population standard deviation, and we got 1.25. So what we would do is we would find 1.2 in this first column. We'd look for the 1.2. Here it is. And then for this 5, right, this is in the 100th place. So we would come over to 0.05, right, because we have 1.25. And then we would come over in our 1.2 row, and we'd come down from this 0.05 all the way to where those two things intersect. And we would get this 0.8944 number. And this 0.8944 is the area under our curve over here, right, to the left. So the z value that we found in our example, remember this is a standard normal distribution, so it's got a mean of 0, a standard deviation of 1. So you go 1 standard deviation to the right, you're at 1. 2 standard deviations to the right, you're at a value of 2. And the z value that we found was 1.25, a little closer to the 1. This would be 1.25. And that 0.8944 number is the area under the curve from from 1.25 exactly all the way to the left under this curve, under this standard normal curve, which is the same area value as the normal distribution from our question. And so this is great, right? This is exactly what we need. We needed a way to find areas under the curve for cutoffs along our distribution that don't fall exactly on a standard deviation. And this is exactly what we've done. Now, one thing before I move on from this slide that's very important to note is that the values inside of this table always give you the area under the curve from your z-value cutoff point, always gives you the area under the curve to the left, right? So it always gives you the area less than the z-value cutoff. So if you have a question, right, that says, what's the probability or what percent of your gorillas live less than 23 years, then you can directly use these values in the table. But for an interval, or if it asks you what's greater than, there's a couple extra steps that we'll have to take, right? So if it were to ask us a greater than, what we could do is just take 1 minus this number, right? If we were to do 1 minus the 0.8944, and remember this 0.8944 is this area to the right. Let me just do it in red so that it's a little more clear. 0.8944. This is the area under the curve to the left of what? To the left of 1.25, right? This z-value cutoff of 1.25 gave us an area under the curve to the left of it from 0.8944. But if our question asked us about the probability of something such as a lifespan, right, being greater than that initial x value that we would have started off with, what can we do? We're only ever given the area to the left, so we still would find this, and then we can just simply take 1, right, because the total area under this curve is always 1. So we take the total area of the curve, which is 1, subtract from the piece that we did find, and what we will be left with is the area under the curve to the right, which is what we would be looking for. So 1 minus 0.8944 is something like 0.1056. Let me just double check that. 1 minus 0.8944 is, yep, 0.1056. And so this would be our answer. This 0.0156 would be our answer if we were asked about something greater than that value. And we'll do some examples of this. If we're asked about a percentage or a probability in between two values, we'll actually have to calculate two different z-values to get the area under the curve of each one. Take their difference, right, to find what's left over in the middle, but we'll do an example of that as well. So here is just a example, right, of a z-table. All right, so in our next video, we'll revisit these questions and do some examples.